Okay. All right, if you're just coming in, please come up and grab a handout or one of my officers will hand out a sheet to you. Thank you so much. Okay, so today is our final lecture on the second part of the class, which is the thermodynamics component. Okay? So starting next week, we are going to be transitioning into the final section, which is the energy balances component. Right? So in a lot of chemical engineering programs, this class is called mass and energy balances. Okay? So we've got the mass balances already covered, but that's obviously going to persist throughout. Now we are introducing additional, basically, design specifications. But instead of the design specification being, this is the composition of the stream, the design specification is now, we have this mixture in phase equilibrium according to this model, or according to this phase diagram. What that allows us to do is to give you less information, and we can rely more on the actual physics of the real scenario. Okay? Then finally, the energy balance aspect is going to be focused a lot on basically just how much energy does it take to heat this up to get to the correct conditions. That, of course, is going to be useful for all of our cost estimation. So if I think that there is a market to produce a particular chemical, as chemical engineers, and this is, of course, the traditional chemical engineering petrochemical angle, which is not the only application, but I need to buy feedstock, I need to understand the chemistry of how to process it, I need to then purify my product, I need to buy the raw materials, I need to build all the equipment, I need to purchase all of the natural gas or electricity that I need to heat and cool stuff down, right? So this is the final piece of this. Now in your senior year, you're going to revisit everything that we covered in this class. But you're also going to have to determine, okay, so if this reactor is this many cubic meters, it has to have this thick of wall of steel with this specialized coating to prevent corrosion, how much is that going to cost to purchase? And then you can estimate, is this a financially viable opportunity, right? I don't want to disappoint you, but probably after this class, you will not be doing many of these calculations by hand. You'll be using something called a process flow simulator. But the concepts that we're discussing of material balances and energy balances, they are very useful tools to help you start basically all calculations. So everything that you're going to be doing moving forward is going to initiate by a material balance or an energy balance. Right? Your thermodynamics class is going to be start off with an energy balance, start off with an entropy balance. Reactor engineering is going to start off with a molecule balance. Right? What is the rate of change of the number of moles of species A? What is the rate of change of the number of moles of species B? The reaction rate constant that tells you how quickly the rate change is going to be provided, and then you introduce the geometry, whether it's a CSTR or a PFR. You guys have heard those terms, right? CSTR? PFR? Excellent, right? Mass transfer. That class starts off with a material balance. But instead of it being a process, it is a differentially small box, dx, dy, dz, right? And then you derive a partial differential equation, and you can solve that partial differential equation to know how things diffuse. The fluid mechanics class is a momentum balance, is your starting off point, right? So balances are the cornerstone to all of chemical engineering. So today we're going to be doing a lot of sort of more practical applied phase diagram discussion, and this is going to be really applicable to help you understand your homework. So I've got a little stuff to talk about on the board, and then we're going to go over the handout that I provided. So the first one, I just wanted to go over the nomenclature. So there's one problem on the homework that discusses the solubility of a salt in water for a crystallizer. So when we use the terms saturated, this is equal to the max or equilibrium solubility. Now, generally, when we think of solubility, we'll think of it as salt in water, sugar in water. But this term, saturation, is a generic term in thermodynamics, right? It can refer to, is the air saturated with water in the case of humidity, right? Is the system saturated in terms of a PXY or a TXY phase diagram? Right? Just because a certain amount of benzene can dissolve in toluene and a certain amount of toluene can dissolve into benzene, it doesn't necessarily mean you have to be at that equilibrium composition. Okay? We can get to environments of supersaturation where we exceed the maximum allowed by thermodynamics. Now, how this happens in thermodynamics is a somewhat more complicated concept. It has to do with the idea of surface tension, and that by creating an interface, it actually takes energy. So it actually can be okay for the system to be a little bit out of equilibrium with thermodynamics because it takes effort to create a new phase, right? So that's why, for example, we use boiling chips in chemistry. Right? Who's taken the chemistry lab? Have you guys used boiling chips before? One person's used boiling chips. 2 people have used boiling chips.
Are those little things?
They're the teeny little sharp, pointy little stones that you drop in the bottom of your.
Like attract bubbles, right?
Yes. So do we know why we use those? Yeah.
To attract the bubbles from those points that are from randomly.
Right. So they serve as what we call nucleation points. Right. So it prevents supersaturation. And in this case, the supersaturation there would be water vapor dissolved into liquid water, right? So water can actually exceed 100 degrees C and not boil because it takes energy to create those bubbles. So if you're a good chemist, and I was not a good chemist, so chemical engineering was a better calling for me, your glassware needs to be impeccably clean, right? Because you don't want to have nucleation sites. If you have nucleation sites on your glassware and you're trying to synthesize nanoparticles, you're just going to get a clumpy glob of metal stuck to the side of your glassware, and you're not going to get nice, uniform, beautiful 10 nanometer gold nanoparticles. Okay? So the problem is if you have super clean glassware with no nucleation sites, that means if you're trying to heat up your solvent, you actually can't. And then if you accidentally tap it or bump it, that'll provide the system sufficient energy to create those nucleation sites, and you have sort of an explosive boiling situation. Right? The same reason why they recommend you put like a chopstick in a cup of water if you boil it in the microwave. Or if you have a brand new pot and pan and you heat pasta water up and you put some salt on it, it'll violently boil over. Right? That's all because you're supersaturating it. So in the homework problem, right, you have a solution that is supersaturated, and then you nucleate some of those crystals. Right? So once you get to equilibrium, this is going to be your maximum solubility. So the difference between how much is being fed that's supersaturated and how much is going to be there at equilibrium, that's going to be the difference that will crystallize out. Right? But I wanted to go through these terms because we're going to apply them in a lot of different ways, and I just wanted to make sure that that was clear. Okay. So the triangle diagram that you guys have seen in your homework, right? We haven't talked about it yet. We're going to talk about it now. But before I do, I first want to introduce what is the importance of liquid-liquid equilibrium. Let me erase this here. So LLE is the little initialism that I use for this. So vapor-liquid equilibrium is VLE, chemical reaction equilibrium is CRE. Hopefully you get the picture. Okay. Distillation is the dominant means of separation that we use as chemical engineers. But it consumes, on average, or approximately 5 to 10% of all global energy consumption. A lot. But look around. Every single thing in this room probably has a product that was produced by distillation, right? It's like a plastic table. Those polymer precursors, the monomers, those have to be separated in the synthesis process, right? Synthetic fibers, coatings, paints, right? Everything that is a liquid at some point very likely was produced in a distillation column following a chemical reaction, right? So that's why it's so expensive, is because absolutely everything, right, is being used in that way. But there's an alternative. The alternative is much harder to design, but much more energy efficient. And that's liquid-liquid equilibrium. So, in an example, let's have fluid A be ethanol, fluid B be water. Actually, let's look here. And fluid C will be benzene. So an example of a highly desirable liquid-liquid separation would be for ethanol production for fuels. Right now, ethanol for biofuel is actually not a very good environmentally friendly option, because we can synthesize the ethanol, right, by fermenting biomass or sugars in an industrial fermenter, but then you have to separate the ethanol from the water, because obviously we're not burning water in our gas tanks. The energy that it takes to basically grow the sugar, ferment it, transport it, distill it, is about the same carbon footprint as you get just by burning the gasoline, right? So let's say if it was possible to eliminate that distillation step, then it would be a much more viable option. So in this particular mixture, we have ethanol, which is organic. We have water, which is inorganic. And we have benzene, which is organic. Now, I'm not saying this is the solution to that particular problem. It's just sort of an example. Benzene and ethanol would just push the problem further down the road. Right? In this scenario, the ethanol and water, these are miscible. Right? So if I have a water and ethanol stream, this is something that would mix together. Ethanol can also dissolve in benzene. Right? So hopefully you guys have heard the term miscible. I mean, can mix, can dissolve. Immiscible would be the case of water and benzene. Right? So water, an inorganic polar compound, benzene, an organic nonpolar compound, they don't dissolve well into one another. So you can imagine a scenario here where you could take a water and ethanol stream. The ethanol can dissolve into benzene, and so you can remove ethanol from the inorganic phase to the organic phase, right? And we don't have to boil it, which is the nice thing. Eventually, then you have to then also remove this. But the ideal way of doing a liquid-liquid extraction is to use, for example, a heavy organic that has a low volatility, and then you're trying to separate an organic compound that has a high volatility. So then this separation between A and C would be particularly easy. Right? So if this boiled at, let's say, 200 degrees C and this boiled at 50 degrees C, then it'd be really easy. You could use a flash separator. You wouldn't have to use a distillation column. Does that kind of make sense? Right? So the problem with distillation columns is that you are condensing vapors to a liquid at the top and you're boiling liquids to a vapor at the bottom, which basically means that you're boiling and cooling at the same time. So it's like opening your fridge and your oven and seeing who wins to keep your house the same temperature, right? That's basically the analogy of what distillation is doing. Okay? So in a liquid-liquid separator, we're first going to start off with what I would say is more like a standard design specification. Okay? Then we'll talk about the triangle diagram. So that is going to be a partition ratio or coefficient. So let me draw the process flow diagram, and then I'll describe what this is here. So if I have a stream coming in that follows a similar example here, where I have A and B, so in this case it could be water and ethanol from, let's say, a fermenter. I then mix in C, a component that is soluble with one but insoluble with the other. I go into a liquid-liquid extractor. Then I'm going to form two phases. Now in vapor-liquid equilibrium, it's very easy because I can call this vapor, I can call this liquid, because those are the two phases. We have names for that. Yes?
What does that say? Is that
IMMISCIBLE. Immiscible. Yes.
Is that just non-soluble?
Correct. But you'll soon learn in thermodynamics, too, that actually everything is soluble in everything. So there is no two things that are completely immiscible. So the example I like to give always in my thermo class is if I took some used motor oil and I put some water on top of it, right, or mix it with water, right? Oil and water don't mix, right? And I shook it up. Would you drink that water? No. Of course. A little bit of the oil does dissolve in the water, right? And the triangle diagram quantifies that.
Drink the oil.
To each their own. Okay, so when we're talking about liquid-liquid equilibrium, we cannot say it's the vapor phase and the liquid phase, right? So Raoult's law is a phase equilibrium expression that relates between the properties of phase 1, vapor, and the properties of phase 2, liquid. In this case, when I have two liquid phases, I can call them phase 1 and phase 2. I can call this one, for example, oil-rich or organic-rich. Right, I'm drawing it on top because the organic compounds are typically less dense than water. And then I can call phase 2, let's, for example, water-rich. Right? And if C is the organic phase, you would want to feed it at the bottom so that it would flow through phase 1 that would dip down. You know what I mean? So you want to mix them together. So that's why they're flipped a little bit. Okay? So when we're talking about liquid-liquid equilibrium, we can call it A-rich and C-rich, or we can call it oil-rich and water-rich, right? Or we can just call it phase 1 and phase 2. Right? But it's not the same convenient nomenclature as vapor and liquid, right? Because we don't have a name because they're both liquids. Okay? Then, leaving the system here, we are going to have, in this case here, B and C. In this case, we're going to have A and B. This is assuming that our A and C don't mix. They're immiscible. Right, so following this example, let's see, how do I fix this? So if A is ethanol, then this one would be,
So why are we using immiscible and miscible instead of insoluble and soluble? Is there a meaningful difference?
no.
Okay.
So in this case, I'm trying to keep my same example here. So A and C, and then this would be A and B. Okay, yeah, there we go. So, in this case, B and C don't mix. Okay. For some reason, past Michael changes nomenclature. So then these two phases here are in equilibrium. So we can use our phase transition thermodynamics to determine how much of A goes into C and how much of A goes into B. Okay? So Raoult's law is the same thing, but the problem is liquid-liquid phase equilibrium is actually very, very complicated, and so it's a bit outside the scope. So we're just going to rely on data that other people have developed. Okay? So the partition coefficient, K, is going to be a design specification that we can use to solve these particular material balances. So K is going to be equal to the mass fraction, in this case, of A in phase 1 divided by the mass fraction of A in phase 2, right? Because we were concerned about getting the ethanol from one phase to the other phase. Yes?
So is this just simply like a Hirsch funnel where you like put the oil, like the organic solvent, mix it, and then do that like a few times?
That is exactly a liquid-liquid separation. Yep. But in this case, they do it continuously. And so how long the separator is going to be the determining factor for how much contact time that you need. And they'll also put in baffles and things like that so that it's well mixed. And then they have a settling period, and then they have a hole in the bottom and a hole at the top. So another really common example of a liquid-liquid separator is an oil desalter. I don't know if you guys have ever heard of that. It's the first step in a refinery. So when you get crude oil, there's going to be a lot of dissolved salts, right? Maybe a lot of like sulfur-containing components. And those salts, so if you heat up sodium chloride, right, in a distillation column for crude oil separation, it actually turns into hydrochloric acid when you heat it high enough. And that corrodes the process equipment, right? So you want to remove all that material. And so you actually mix water with the oil. The salts will dissolve into the water phase. The problem is sometimes oils have surfactants like soaps, and that can create emulsions. And then you get what they call a rag layer of this emulsified oil and water mixture that they have to add chemicals to break up. Otherwise, you'll get water in the oil phase and oil in the water phase, and no one's happy. Right? Because then you have an environmental cleanup issue, and you also have, basically exploding water in your refinery because you heat these up to a couple hundred degrees. Yes?
You were saying that like the oil can have soap that causes emulsification, like natural soap?
Yes, surfactants. Yep.
Huh. Didn't know.
So naphthenic acids are a really common one. So they're acidic groups in the crude oil.
Wait, so what exactly is a soap?
So a surfactant is commonly drawn in chemistry like this, right, where you have a hydrophobic alkane tail and some sort of a hydrophilic head, right? So this could be a phosphate, a sulfate, an alcohol, something like that. So what this does basically is if you're trying to remove grease off of your hands, like if you're working on your car or changing your oil, right, water and oil don't mix particularly well. But if you put soap on your hands, right, this part will stick to the oil on your hands, this part will stick to the water, and you can help release that. Right? So that's what a surfactant accomplishes. So there's still a lot of research into surfactants, very fancy ones. Pluronics, right? So I think the solutions that people use to clean their contact lenses are a very fancy surfactant called a pluronic, which is a tri-block copolymer. So it's a long polymer chain with 3 functional groups that all hate each other, right? And so they form a nanoparticle that's called a Janus particle with a core. So this is part A, this is part B, this is part C. And it forms a really big clump, and it's a very strong surfactant. So this is called a pluronic. So, fun stuff. Okay, so then here, of course, in the partition coefficient, the mass fraction of A would be the mass of A in phase 1 divided by the mass of A in phase 1 plus the mass of C in phase 1 divided by the mass of A in phase 2 divided by the mass of A in phase 2 plus the mass of B in phase 2. Okay? So not the easiest design specification, right? But again, it's all algebra. It's all algebra. So keeping a clear and consistent nomenclature with liquid-liquid equilibrium is going to be just as important as keeping a clear and consistent nomenclature when you have 5, 6, 7, 8, 9, 10, 20 different flow streams, right? So a real chemical process is going to have potentially hundreds of flow streams and hundreds of energy streams, right? Steam flow rates, electric heaters, pumps, all these different pieces of process equipment. Okay. So what this information is quantifying is liquid-liquid phase equilibrium. Now, before we transition to the phase diagrams, I just want to go over really quickly the PXY diagram. Right, the PXY, I think, is the easiest to conceptually solve for and discuss. Okay? Okay, at high pressures, what phase am I in? Liquid. At low pressures, what phase am I in? Vapor. So this line here going from liquid to the 2-phase is called what? This is the bubble curve. The bubble curve tells us information about the liquid phase composition. Going from vapor to the 2-phase region, this is our dew curve. The dew curve tells us about the vapor phase information. So then I'm going to draw a horizontal line, right? Remember, this slice is constant temperature. This line is constant pressure. So I have to have constant temperature and constant pressure to have my phase equilibrium work out. So that means that the intersection of all of these lines, a plane of constant temperature, a line of constant pressure, these two solutions here are the solutions to Raoult's law. The bubble curve point tells me the composition in the liquid phase. The dew curve tells me the composition in the vapor phase. Now this is really straightforward to understand because it's a horizontal line. But this line right here is called a tie line. The tie line connects the composition of phase 1 to phase 2. In liquid-liquid equilibrium, we have phase 1 and phase 2. So we should expect there to be a tie line if we are able to plot this information. Okay, this is where it's going to get confusing. So now we're going to go to our handouts, and I'm going to get my computer plugged in. Display to on. Okay. Okay, we have here a triangle diagram. So for folks at home, you'll just have to follow along. This is on the Canvas page. So the triangle diagram is an A, B, C, right? We can't plot it nice like a PXY diagram because it's got more material in it than just an A-B mixture. Now we have 3 components, so we have a 3-sided figure. If you look closely, not all triangle diagrams will have this, but I have this one as an example to help us out. So you'll see from A going outwards, you have 90, 80, 70, 60, 50, 40, 30, 20, 10, 0. Okay? So if I am at this point, right at the corner here, I am at 100% A. If I go over here to the corner in the bottom right, I am 100% C. At the top, 100% B. Right? I can mix these 3 materials in any composition that I want. Dead smack in the middle, right? I see 30, 30, 30, right? So what's 1/3? 33.3333%. Okay? The tricky part here is that the closer you are to any particular point, right, the more of that material you have. So this is just the general way that we read a triangle diagram. So if I'm along this point, A to C, right, this line here is only a mixture of A and C. This line here is only a mixture of B and C. This line there is only a mixture of A and B. Okay? So now I'm going to show you what a real triangle diagram looks like for a real fluid. We'll come back to that one. So this is a butyric acid, water, and decanol system. Okay. This one's labeled a little bit differently. Okay, they don't have the lines there, but the same information is provided. Okay? So let's look at this diagram here. Are the water, so like I said, let me go over this before I ask questions then. This curve that we see here, this is the solution to our multi-component, multi-phase thermodynamics theory. So liquid-liquid equilibrium is very, very complicated, and so the mathematics to develop this are non-trivial. So most of these are developed experimentally. That curve that you see in this diagram is the same thing as these two curves here. The nomenclature is just different. Bubble is for liquid, dew is for vapor. This horizontal line is a tie line. It connects between the phase 1 and phase 2. These lines that we see inside of this curved space are also the tie lines. Okay? So if I look at this phase diagram and this butyric acid and decanol, are these two fluids miscible or immiscible? Butyric acid and decanol. Why do you say immiscible?
Because I would imagine that if they were miscible, then the curve would be like two-phase region curve would be closer to the right side where we have just decanol and butyric acid.
Okay. Is there anyone for team miscible? Why do you say they're miscible?
Well, his point's correct that the closer it is to that line, the more miscible they are. But if you just go down to the bottom, they're almost like with a tiny amount of water, you can still get a large amount of.
So
with a tiny
water.
amount of water, you could still get the 2 dimensions.
Yeah. So water doesn't exist in this scenario right now. Just the decanol and butyric acid. So if I were to mix any composition of butyric acid and decanol, I would be following this right side of the triangle. At no point do I ever intersect a phase boundary here. So that would mean that decanol and butyric acid are miscible. In this case, they are infinitely miscible. There is no composition that I can make such that they don't mix together, because I never run into a phase boundary. Question?
Sorry, is this document on your Canvas page?
I think so, yes.
Do you know what it's called?
Triangle diagrams, I think. Yes.
The phase boundary, is that like?
That's this curved region right here, which is the same as this curved region here, right? So, for example, in this PXY diagram, if I pressurize my system to here, my fluids are now miscible, right? From here to there, I never cross a phase boundary. Miscible. But if I lower the pressure and I change the thermodynamics, I will come to a point where they're no longer miscible, and they will form a second phase, which is a vapor phase. So if I were to change the temperature of this triangle diagram, let's say I were to lower the temperature, you may find a phase boundary developing between the butyric acid and the decanol. But at the temperature that this was generated at, those two fluids are miscible. So I'm trying to draw as many connections as I can from vapor liquid to the liquid liquid.
So if this curve landed on the triangle lines, that would mean they're immiscible.
So if you were to have, and you could have very complicated triangle diagrams. So you could have another curve that goes from here to there, for example, and that would be a two-phase boundary for liquid-liquid separation between butyric acid and decanol. I'll try and find some more examples from a thermo book if you'd like. Okay? Now, water and butyric acid at this temperature are miscible also, right? I don't ever cross a phase boundary. Water and decanol are immiscible. Okay, is it making sense? The maximum solubility of water in decanol, okay, so I'm only on this bottom curve right here, okay, would be somewhere on the order of where this line intersects the axis here. Right? So if I were to put a 50-50 mixture of water and decanol together by mass, okay, I would then phase separate into a phase that has this composition and a phase that has this composition.
That's decanol and water and decanol, right?
Yep. So that's for two components. We're starting simple with two components, okay? Now that's exactly the same analogy as if I were to go to my PXY diagram. If I were to mix a system at this condition, I would phase separate into two phases, a vapor phase with this composition and a liquid phase with this composition. Questions?
So anywhere out of that curve, we have one phase. So we have
Correct.
two phases.
Yep. And how you know that is that there's no tie lines because you're not having to direct us to different compositions. Right? So I'm just trying to draw parallels between here, which is a nice algorithmic way, and here. Now the lines are curved. The chart is a little bit more confusing, but the way to read it is actually exactly the same. Yes?
So what about that little region near the top where we just stopped drawing?
The experimentalists did not quantify that particularly well, is what I would say. So how these are made, right, is what I would do if I were doing this in the laboratory, is I would take butyric acid, water, and decanol. I would mix them at different ratios, shake it up in a can, wait for it to phase separate, take a sample of phase 1, take a sample of phase 2, and I would measure the compositions. So what I would get is that I would mix up a solution at this composition, this composition, this one, this one, this one, this one, this one, this one, this one. So for example, I would assume that these authors did 9 different experiments, okay, on these 9 different tie lines. And then they measured these 2 data points, these two, and they measured those curves, okay? Because this is the composition of phase 1, this is the composition of phase 2. Does this one have to be phase 1 and this one too? No, this could be phase 1 and this could be phase 2. This is the water-rich phase. This is the decanol-rich phase. Yes?
Do you read the weight percent from this side for decanol or this at the bottom?
So, this is a good question. I had people make this mistake when I've given this figure for exams before. The corner is 100%, right? It's winning the tug of war. So this 0 is obviously 0 decanol, 100 decanol, okay? This is 0 butyric acid, that's 100 butyric acid. This is 100% water, that's 0% water, okay? Yes?
For homeworks, do we just like, if we need to use one of these charts, do we just like approximate where we think it is about, or?
Yes, so good question. So first, okay, so do we feel confident on what the tie lines are communicating to us? Okay, so I just want to go back really quickly and do one more quick thing just so we can read it, and then I'm going to pop back to it. Okay, point 1. What is the composition of the mixture at point 1? Take a second, try yourself out. Let me look at myself so I can figure it out here. Okay, point 1. Okay, I got it. What is the composition of the mixture at point 1?
Is the content of A 10%, content of B is 60%, and the content of C is 30%?
Yes, correct. Okay, so let's go over that answer. So this dot is the closest to B. So we know intuitively it should be the most B. So we look, 90% B, 80% B, 70% B. It's on the 60% B line. Okay? If we look at C, 90, 80, 70, 60, 50, 40, 30, 30% C. And then for A, 90 to 10. Okay? We good? Now, let's do point 3. What is the total composition of the system at point 3, I? And then as a follow-up, what is the composition of the two phases that form? So point 1 is an example on the PXY diagram as being like up here, 100% liquid, or down here, 100% vapor. One phase, infinitely miscible, right? There is no multiple phases that form up here. Points 2 and 3 would be, let's say, for example, a point here and a point here. Okay? So first, let's determine where point 3 is located as a total composition. Now, point 3 is inside of the two-phase envelope, so it'll phase separate following the tie lines to phase 1 and phase 2. Okay, so take a second and try and work it out on your own. And I'll try and work it out on my own too.
Wait, so is outside of the curve is liquid and inside of it is all?
It's all liquid.
All liquid.
But this is outside of the curve is one phase miscible. So in this case, B and C don't form two phases. B and A don't form two phases. A and C don't like each other, and they only have a limited solubility of one inside the other. So inside of this region, this is the two-phase region. Inside of this envelope here, that's the two-phase region. Yes?
So you physically see like two different liquids like sitting on top of each other?
Correct.
Oh,
Yes.
okay.
It'll be like a jar with like oil and vinegar,
So if they mix,
like salad dressing.
if they mix as one base.
Correct, yes, yes. So, for example, this could be a mixture of water and ethanol, so vodka, single phase, right? This could be a vinaigrette dressing, oil and water, right? They would phase separate, so you got to mix it up before you put it on your salad, right? So two phase, oil and water, one phase, one liquid. Point 3. Okay, so let's work through point 3 here. So I'm looking at my chart, and if I look at point 3, this is on the 50 line for A, so it's 50% A. And then for B, it is just above the 10, between the 10 and 20. So it looks like it's about maybe 12% B. So that means it should be 38% C, right? So let's look at the C. So it is a little bit in between 40 and 30. So yeah, that's about right. Right? About 38% C. Does that make sense? The confusing part is it's a little bit backwards, right? So the numbers are kind of counting down as you go away. So you just kind of have to do that little flip in your head. Okay. So now let's look at what is the composition of the phases that form. So let's call this one the C-rich phase, right? So this is the tie line. So when people do these experiments, they mix up total mixtures of these compositions, and then they measure the compositions of the phases that separate. That's how you physically do these experiments, and then you connect the two phases with a tie line, and then you work from there. Okay, so this point right here, let me look through it. So that is about, I would say, about 67% C. Are you guys seeing that on your chart? Okay. And then for B, it looks like it is about, maybe 20.5% B, maybe about. Does that work? And then for A, it looks like it's about 11-ish.
Wait,
12-ish.
B just to 20.1.
So there's going to be some degree of subjectivity in reading these diagrams. So I am cognizant of that when we do exams and homework problems. But getting a ruler out and actually kind of estimating what percentage it is between those lines gives you a way to do that. Does that make sense? But make sure they add up to 100. But there may be some slight differences in people's answers. Okay? So that would be the composition of the C-rich phase. Now the A-rich phase, again, I would go to this tie line, follow it all the way down to here, to that point. So if I'm looking at that point, it looks like it is about, I would say 93% A, right?
Wait, isn't that below below being above the 9? Oh, I'm looking at the wrong.
Yeah, so the corner is 100, and the next line is 90. So I'd say we're about maybe 92.5, maybe 93% A. Okay, and then for B, not a lot of B in there. So it looks like maybe 4% B, right? Because this line between A and C here is 0% B. So that means the balance on C, it looks like it's about 5 or 6% C. Now, to give you a more precise answer, I'd have to bust out my ruler. How do we feel about reading the triangle diagram? Good. Does the concept of this being a tie line, which is straight and looks organized, and these being tie lines that are curvy and disorganized, is that okay? Okay. Now, point 2. What do I do at point 2?
The same thing we just did.
Right, but there's no tie line.
Estimation.
Right? So how do we draw the tie line? Do I draw it parallel to this top line? Do I draw it parallel to this bottom line? No. I have to draw a tie line that perfectly sort of matches the same relative position as the point that I'm trying to go to, right? So for example, here, right, see how that kind of pinches together here and it kind of expands out there? So this point 2, I would say is maybe, if I'm looking this way here, I would say it's maybe like 60% from the top line and maybe 40% from the bottom line. Does that seem about right to you guys? So that means my tie line would need to connect the points. That's about 60% down from here and about 60% down from here, right? So I want to think of this like a fan opening up, not just shifting this one parallel and shifting this one parallel. Okay? So that is how we read the triangle diagrams. Question?
If you had a dot like on the curve, would it still separate into two different ones, or would it just stay on the line?
Very good question. That is exactly equivalent to the bubble curve and the dew curve. So you would be right on the precipice of a cliff. If you add a little bit more, you'll phase separate. So for example, a common question that I like to ask to test if people understand what these diagrams have is I will say, right, so be prepared, this might be a quiz exam question. I have 100% pure C. I am going to slowly titrate A into the system. At what composition will a second phase form? Okay? So I have 100% C. I'm titrating A. So should I go this way?
No.
Should I go this way? Should I go this way? Yes. Okay, so I add a little bit of A, a little bit of A, a little bit of A, and I hit the phase boundary. That's when a second phase would form with a different composition. Same thing applies with the lever rule, right? So if I'm at this point here, I'm going to separate into phase 1 and phase 2. Is there going to be more of phase 1 or more of phase 2 in the system? More of phase 1. It's a tug of war. It's winning the tug of war. Right, but the compositions don't change. Question?
And so when you're doing that tug of war, do you like measure the distance between each one and say, okay, this is 5% of the distance, it'll have 5?
Correct. So that's the lever rule.
Yeah.
And perhaps on Monday I'll just give you guys the lever rule equation. But you can just do it with material balances. But when you're reading the subjective triangle diagrams, that's when it comes helpful. Okay, the last thing, right, if I have a 50-50 mixture of B and C, and I slowly titrate A, how much A can I add to the system before a phase transition occurs, and what is the composition of the new phase that forms? Okay? So 50-50 B and C mixture. So I would start off at the 50% line, and then I would slowly add A, so that I would be going straight from here to A, and then at that point, I could read off the composition of how much A there is. Then I could create a new tie line that goes over here, and I could figure out how much that one is. Right? So we can solve a lot of problems just on the triangle diagram. Okay, but the last thing for the homework, right? All of this still needs to go into material balances. Once we get the mass fractions, we still have to balance the whole process. Right? So this is just a way to get more design specifications. And with that, we conclude our thermodynamics for phase equilibrium portion of the class. So section 2 in the books, the exam is going to be the week after we get back from spring break. So a little time to do some homeworks.
Wait, you have another exam?
We have 3 exams and then the final, so 4 exams.
We have another one after spring break.
The Friday after, so we have a whole week after spring break.
I feel like we should
So we have one Friday after class after spring break, and it's the Friday.
No, we have Friday next week, spring break, and then the following Friday is the exam. So it's 3 weeks from today. But like, there's not a lot of class between then and now. Okay, all right.